You are listening to the Effective Statistician podcast, episode number 58, How to Best Analyze Ordinal Data, Overcoming the Simplification Strategy. Welcome to the Effective Statistician with Alexander Schacht and Benjamin Pieske, the weekly podcast for statisticians in the health sector, designed to improve your leadership skills, widen your business acumen, and enhance your efficiency. And in terms of leadership skills, we have an upcoming webinar, Mastering the Art and the Science of Influential Communication for Statisticians. And this webinar happens on May 30th, and you can register for the webinar on the homepage of the Effective Statistician. Just check out theeffectivestatistician.com/webinar. In our webinar, you'll learn about the challenges statisticians face when communicating and what are the keys to being more influential when you communicate and how you can prepare for challenging audiences and why it's so important to have a strong start of your presentation. And finally, we'll give you 3 things you can do now to improve your communication. So don't miss this opportunity to become more effective at work and reduce your frustrations about not being heard or understood. So, in today's episode, we will go into analyzing ordinal data. And what usually happens is that we dichotomize it or we look into continuous data, and that is an oversimplification. Another aspect of ordinal data is that it has now got more attention due to the composite strategy for estimates. And we'll talk about that in a future episode with Michael O'Kelly. So Benjamin and myself will talk today about different ways to analyze ordinal data, because we have been passionate about that already at university and did research there. The podcast is created in association with PSI, a global member organization dedicated to leading and promoting best practice and industry initiatives. Join PSI today to further develop your statistical capabilities with access to the special interest groups, the video-on-demand content library, free registration to all PSI webinars, and much, much more. There is a reduced rate at £20 for non-high-income countries, and it's only £95 for high-income countries. So that's a very, very easy, low-brainer to become a PSI member for a year for that fee. Just visit the PSI website at psiweb.org to learn more about PSI activities and become a PSI member today. Welcome to another episode of the Effective Statistician podcast. And today we have a technical topic. As lots of you requested to have more technical topics, this is exactly the episode today. And I'm speaking again with Benjamin about that. Hi, Benjamin. How are you doing?
Hi, Alexander. Well, tired, but otherwise it's fine. Yeah.
Yeah, your voice is a little bit rough today, so we said I'll do a little bit more speaking today and go through this topic today, which is actually very, very close to my heart, because it's one of the topics that I did some research in and took a lot of time during my time at university to look into it. And the topic of today is analyzing ordinal data. And ordinal data is something that comes across our day-to-day business quite frequently. However, very often we actually don't treat it as such. And usually ordinal data comes in the form of ordered categorical data. And so that could be, there's lots of different examples for that. Everybody, of course, is familiar with kind of school classes, school grades that are categorized A, B, C, D, E, or 1 to 6, or depending on the school system, and reflect ordered categorical data. So you can always say one grade is better than the next grade, but you can't really say what's the difference between these.
Yeah, well, difficult in school at least to say what's if you get a 1 before 2, it makes 2 very good grades. So no, it's true. So you can't multiply or sum them up or whatever. You can't really use them as normal data. I mean, it's easy. It's obviously for grades like A, B, C, D, E, whatever. So this is because obviously you can't calculate with them. But if you have numbers, people might get confused with it.
Yeah, and a very, very kind of usual thing in clinical is, for example, the CGI, the clinical global impression of whatever severity you're looking into, which is often measured from 1 to 7, and you have anchors for the 1 and for the 7. In terms of the disease, the worst disease you've ever seen to no symptoms at all, or something like this.
Yeah.
And the problem with that is actually that very often people confuse these numbers with real numbers, saying that, the difference between 1 and 2 is the same as between 2 and 3 and 3 and 4 and so on, and forget that these are just representatives of states like no disease, mild symptoms, moderate symptoms, severe symptoms, very severe symptoms. And of course, you can't really say that the difference between no symptoms and mild symptoms is the same as between mild and moderate symptoms.
Absolutely. And it's also for example, if you have polls, you always have been asked, how did you like the conference or whatever, and you say very good, satisfactory or bad, or this is kind, you can't use them like this. And especially when it gets into our programming language, or when we have use SAS, we usually have numbers behind it, and we have formats on it, so you read it, but you can calculate it. But no, you can't.
Yeah. And there's even some special cases where you have continuous ordinal data. So if you think of a visual analog scale, that, for example, is could be seen as a continuous ordinal data. So where you can say, okay, mark your pain on this visual analog scale between 0 and 100 millimeters. And then that, is also actually not a metric. It's just a number that describes the pain. But you can't really say, well, the difference between 0 and 10 millimeters is the same as between, let's say, 80 and 90 millimeters. Yeah, it's a completely different range.
And a different meaning, a different pain.
Completely different pain. Yeah. So these are just a couple of examples to help you understand what we mean by ordinal data. And usually we have for these things, the problems, and we want to look into changes from baseline versus endpoint. And sometimes you only have this assessment at one time point, but very often we look into changes from baseline versus endpoint. And that, of course, in itself brings some problems. Yeah, because you want to make a comparison there and calculate a delta, which is actually in the first place not possible.
Yeah, I mean, it's just from what we just said. It's if the change, maybe the same difference, even it's not a real difference, but it's the same difference, but it's a different meaning. So, I mean, on the one side, you can easily say, okay, it's getting better, it's getting worse. So that is regardless of what category it is, but we can't really quantify overall, over the full scale, we can't quantify a change from baseline, let's say.
Yeah. And there's another kind of problem is that if you look into changes, of course, imagine you have a CGI with 1 to 7. Well, if you have a 2 at baseline, you can't have a change of -5.
It's true.
so there's a lots of kind of problems associated
Limitations.
with these kind of things. However, you very commonly you see that ANOVAs, MMRM, so mixed model repeated measures, or t-test, or any other kind of linear models are used in these kind of settings. So the problem with that is that it actually doesn't respect the baseline information that is actually in the data.
Yep. No, what is then the best way of using the data?
Well, let's say the easiest way is to look into responses. And, that is very, very often done because people like to use binary data. So they look into, as you said, have they improved? Yes or no, so to say. Yeah. Or did they improve below a certain threshold? Yeah. So how many patients had at max moderate disease at endpoint? When maybe moderate disease or severe disease was a baseline inclusion criteria. So that way you can you kind of try to get around it by dichotomizing things, and that's of course at least it takes into account that there's an ordinal variable here. So, and then you can, use all your usual approaches like logistic regression or, Fisher's test or, all the things that you do with binary variables.
Yeah, but at first sight, if you just decrease the meaning of your questions to a binary question, isn't this a loss of information?
Yeah, of course. There's a lot of loss in information, and especially if you don't have so much data, in smaller studies, that loss of information can be quite terrible. And also in bigger studies, maybe it's easier for you to interpret, but of course, let's say you have a baseline inclusion criterion that your CGI needs to be at least, 4, let's say, and you look into your CGI response as something that is maximum 3 at endpoint. But of course, it makes a huge difference if you just moved from a 4 to a 3, or whether you moved from a 7 to a 3. Yeah. Yep. And so you're throwing away that information, or whether you have moved from a 7 to a 0 versus a 4 to a 3. Yeah, both are responders, but one is a really dramatic improvement, and the other thing is,
slight improvement or just
just noticeable, and or maybe it's just random variation over time. So that's where the problem is. So with these binary approaches, you can of course have look into logit and probit link models, and all these kind of things. Another topic that you can do is if you have just the endpoints that you're looking into, is a proportional odds model. So you can basically treat all these categories as ordered, and the proportional odds model is basically a couple of logit models layered over each other. So let's say you have you're looking into CGI with 7 categories, 1 to 7. Then it looks into the dichotomization 1 versus bigger than 1, 2 versus bigger than 2, 3 versus bigger than 3, and so on up to below 6 to versus 7. So you get all these odds, and the assumption of the proportional odds is that your effect for your covariates doesn't alter depending on the odds ratios you're looking into. So if you think of a logistic regression model, it has this alpha plus beta times covariate linear term. And the beta times covariates, that stays the same, and the alpha just changes for the different thresholds you're looking into. So there you would, instead of having 1 threshold alpha, you would have 6 1. Yeah. And that's a very, very strong assumption. And you can check that visually, whether these log odds ratios really hold. And that's quite a nice way to analyze these data in a parametric way, because then all the techniques that you know from logistic regressions, they can mostly be transferred to this proportional odds model.
You mentioned the visualization for this. I mean, it's difficult in a podcast maybe, but how can you look into this?
So basically, you run logistic regressions for each of these dichotomizations that I just mentioned, and then you check whether the odds are actually the odds ratios are actually stable, and
okay, so
that helps you. Yeah. The downside to that is that, on the first, this assumption needs to hold. And the other thing is, if you have sparse data on a couple of categories, especially on the lower and upper end, you get into more problems. Yeah, because there's the calculation becomes a little bit unstable.
Okay.
Yeah.
Oh, interesting. So you just learned something.
Yeah, and of course there's there's SAS functions and R functions for these kind of things. So just check that out. Another approach, which is actually a very, very nice approach to analyzing this data, is based on ranks. And this is where both Benjamin and myself got a lot of experience during our time at university, because Professor Brunner published quite extensively about that, has written a couple of books on rank-based methods for factorial data, for covariate adjustment, and things like that. And what it basically does, it looks into the data just from a rank perspective. And all these methods are basically extensions of the Wilcoxon-Mann-Whitney test.
Yeah, and it's a good thing. I mean, we are now talking about ordinal data, but just to come back to the rank topic, is really that whatever data it is, it works. So it's not necessarily only for ordinal data, so it's really for any other data. But it's just that, if you order them based on ranks, you see that the differences that we couldn't interpret before, we can't interpret in ranks either. But that's the assumption for it. So that's why it now works.
Yeah, but with the ranks, you get a mean rank for one treatment group and a mean rank for the other treatment group. And that gives you a perception about the difference between the groups.
Yeah.
And what you can even do based on these mean ranks, you can also calculate the probability that a randomly taken subject from treatment A is better performing than a randomly subject treated from treatment B.
Mm-hmm.
And that is called the relative effect. Not the effect size, the relative effect. So the probability that a subject given treatment A is better than subject treatment on B. And of course, if that probability is 50%, both treatments are called relatively equal. So their mean ranks would be the same, and the could be just the distribution would be just different in terms of the standard deviation, but kind of the mean rank would be the same.
Hmm.
That's also called the Behrens-Fisher problem. Just a little side note. And then if you have this relative effect of 1 or 100%, then basically the worst patient on treatment A is better than the best patient on treatment B. So you have complete separation. Yeah. But then you don't need stats, actually.
Well, that's true.
Yeah. And there's also a couple of nice ways how you can, if you have, for example, binary data, or if you have really kind of continuous Gaussian distributed data, normal distributed data, you can also see how, response rate difference or mean difference, how that would translate into this relative effect. There's nice publications about that in the books by Brunner, but I also have an example of that in the papers that I published in Biometrics, and I'll cite that in the show notes. So just check out the show notes. We'll have a couple of links there to SAS macros, to R macros, and other things to give you a little bit more background in terms of these rank-based methods. So we just talked about kind of the two treatment case scenario where you would have a Wilcoxon and Whitney test. But there's also extensions of that where you can use covariate adjustments. And this is completely non-parametric. So each, for example, the baseline variables that you have in your data set, you can take that as a covariate. And if you have randomized treatments, then the interpretation of the outcomes, the relative treatment effect that is adjusted for covariates, is completely the same as in the Wilcoxon and Whitney test.
Yep, and you'll also find these in the books from Professor Brunner, for example, and others, where there have been a lot of publications or a lot of thoughts around these topics and the non-parametric approaches.
Yeah. One other thing is you might also have a couple of treatment groups. So let's say treatment A, B, C. And there's rank-based methods here as well. Just the interpretation of the relative effect becomes a little bit more tricky, because basically what you do is you get for each treatment, you get a relative effect that tells you something about how it compares to all the other treatments. So, and then these relative effects are, really depend on what other treatments you are comparing them to. So that is one of the key things. It's always about relative. Yeah. So you don't get an absolute outcome here, which is one of the limitations, of course. There's one other thing that was also published in the 90s. That is the so-called Van Elteren test. The Van Elteren test looks also in rank-based methods and looks into that for each category of the endpoint at baseline. So basically it looks into, let's say, for all those that have a CGA of 7 at baseline, what is there's a Mann-Wilcoxon test. Then for all which have a 6 at baseline, what is a Mann-Wilcoxon test? And then for all those with 4 and so on. So basically you get for each category at baseline, you get a Wilcoxon-Mann-Whitney test, and Van Elteren, they proposed a method how to combine these. However, there's obviously some problems there. First, with the overall interpretation there, and second, if you have sparse categories, then that becomes really, really unstable. So you probably need to combine categories at baseline, and that's really bad.
You already mentioned that about how to use computer programs for these testings, but what is your preference there? I just remember that it's been a while though, but that the non-parametric approaches have been quite tedious to do in SAS. So it was possible with some workarounds and everything. So, but what is the status quo then today for what would you recommend then to use?
I probably would go for R, because nowadays most of the publications in that field are published together with R code. And so we'll put some references to R codes in the show notes. So you can download these R macros there. And by the way, we are planning to have a very, very special guest on the topic of non-parametrics in the future. So stay tuned. We are not yet revealing the name, but it will be quite exciting to have him
indeed.
As a guest. Yeah. So one other thing, as I said, the problem is with non-parametric data, or with all these approaches, is how do you communicate these data effectively? And what I really like is visual displays like stacked bar charts here. So that's a nice way to look into it. These where you have colors going from yellow into red, and you have different degrees of red and yellow to show the severity.
Yeah, that brings me back, or reminds me of a topic about, say, what a nice graphic shows more than 1,000 words, or tells you more than 1,000 words. So it's really about, it's a good point again to bring it up, is that carefully consider how you present the data and how this is done. And as Alexander said, colors and stacked bars, it's a very good approach for interpreting or summarizing, showing the results.
Yeah, and there you can basically see also where the differences happen. So if you just have let's say, a response variable, how many people get below 3 or something like this, you have, just these 2 bars, but you don't see, where all the other categories happening. And is this below 3 for one treatment? Is this mostly 0? Or is that, mostly 1 and 2? And of course, these things really have a lot of impact. So especially if there's bigger treatment differences, that can be quite interesting to look into. Another point is if you have many time points over time, you can also even animate these stacked bar charts. So you can, interpolate the data and see kind of where over a certain period of time people will likely move over into the next category. And by that have, animated stacked bar charts over time, and which gives you a nice way to visualize how patients are progressing from baseline to endpoint.
That's an excellent idea. I've never seen such, moving, living bar or graphic in that content. So it's a very good idea indeed. Mm.
Yeah. Oh, and most of the journals nowadays accept these kind of electronic video formats as an electronic appendix. And also for conferences, of course, it's a great way to present the data. It's much more appealing than, just showing bar charts like, everybody else.
Excellent. There's one point that about how do we handle missing data for ordinal data? So what are the downsides there, or what you need to recommend to take care of for handling missing data?
Yeah, I think there is the kind of same problems that you have for most of the data. Here, one of the good things is, the kind of worst outcome. And so one of the things that you can handle missing data, so especially kind of missing data arising from dropouts over time, you could, assume that they have the worst outcome or, the last outcome, depending on, what you're looking into. And that's just one way to analyze the data.
Excellent.
Okay, very good. I think with that, we have a short but very, very technical presentation today. And I hope that gives you a little bit of input into your day-to-day work and gives you some opportunity to analyze data differently, to step out of what has been usually done and then to look into better ways of analyzing the data, presenting the data. Just one thing, I would never call these kind of non-parametric analysis kind of sensitivity analysis to the parametric ones, because they're really not sensitivity analysis. They're looking into very, very different effect measures, and you can't say really if one is, let's say, significant and the other is, not, let's say, inconsistent or whatsoever. Really, they look into different, very different ways of the data, and understand that is really crucial.
Yeah, and that actually is one of the topics then for the non-parametric ones, to compare the way of using non-parametric methods compared to parametric methods. And maybe we have some more thoughts then on that podcast episode coming up.
Yeah, and on communication of these non-parametric approaches. Okay, thanks so much for listening today, and tune in next week. And if you have enjoyed today's episode, please send us a reply and tell your colleagues about it.
Bye.
Bye. This show was created in association with PSI. And next week we will talk about pre-specification, another very, very interesting and relevant topic for our day-to-day work. Thanks for listening. And don't forget to register for the webinar about communication and how to be a much more effective communicator as a statistician. Just register under See Effective Statistician /webinar today.